Hello and welcome back to another episode of Math with So. And today we're going to be doing a good one. It is the factor remainder theorem. Okay, so this is the idea that when you use synthetic division, that the remainder of that would tell you if it divides evenly and is a zero or a factor. Okay, so for these problems, I consider them the hint problems where you're given a factor and you're asked to find the remaining factors, or you're given a zero and you're asked to find the remaining zeros. Okay, so all we're going to need to do is things that we've already learned, which is divide, change the sign of the x plus 1 to a negative 1, and then we're going to bring the 2, the 15, the negative 11, and the negative 24 right here, and we're going to do synthetic division. Now, if we do this correctly, this has to have a remainder of 0. So we bring the first number down 2, then we multiply 2 and negative 1, we're going to get negative 2. Add straight down, we're going to get 13. Multiply, we get negative 13. Add straight down, we get negative 24. And then when we add these, multiply these two, we get 24 and then 0. Okay, so we got the remainder of 0. That has to happen, all right? Because it divided evenly, we know that this is, in fact, a factor. And for all of these, we're trying to get it from an x to the third to an x squared, because pretty much anything with an x squared is factorable, or at least solvable with the quadratic formula. So that's what we're going to do here. We're going to take the 2x squared, the 13x, and the 24, and we're going to factor a little bit further. So we multiply 2 and 24 together. 2 times 24 is 48. What multiplies to 48 but will add to 13? And I have a feeling that that is 6 and 7. So 48 divided by 7. Not 6 and 7. 48 divided by 4 is 12. 48 divided by 3 is 16. There we go. 3 and 16. There are the winners. 3 and 16 will add in some way or subtract in some way to get to 13. So we're going to write an x plus 16 and an x minus 3 to do that, because those two numbers multiply to the 48, technically negative 48, and add to positive 13. But because we multiplied by the 2 in the beginning, we have to divide by 2 for both of these. If you're solving, you can just change the signs and you get negative 8 and positive 3 over 2, but we're not solving. So we have to write what does divide as x plus 8 and what does not divide as a 2x minus 3. These would be the remaining factors. Okay? So another factor problem. We got given x minus 6 as a factor. Find the remaining factors. We change the sign of the 6. We got a 1, a negative 4, a negative 47, and then a 2, 10. I'm betting this is going to operate the exact same way. We bring down the 1. We multiply. We add. We multiply, we add, and when we take 35 and multiply by 6, we get a negative 210, which gives us a remainder of 0. It has to have a remainder of 0 if it's done correctly. Again, we're going from x to the third down to an x squared. So we got x squared plus 2x minus 35. What things multiply to 35 but add to 2? 7 and 5. I think that's the only things that really multiply to 35. So we got x plus 7 and x minus 5 as the remaining two factors. We didn't multiply by a number in front, so we don't need to divide by 1 right here. Okay? The next phase is going to be given a 0, find the remaining zeros. So virtually the only thing that is going to change here is if you are provided a 0, do not change the sign for your synthetic division. You keep the negative 1, negative 1. It's not a factor, it's a 0. If you had a factor, the factor would be x plus 1, because the factors and zeros are opposites of each other. So we got 1, 2, negative 1, and negative 2. And then we do our synthetic division. We bring down the 1, multiply and add, multiply and add, and multiply and add. And we better get a remainder of 0, which is another indication that this is a 0 and divided evenly. So from this point, you set it equal to 0. We should be able to factor the majority of these, but if it doesn't factor, you have to use the quadratic formula or square rooting or something like that. And in this one, what multiplies to negative 2 but adds to 1 is going to be positive 2 and negative 1. So that would multiply to negative 2 and add to positive 1. But again, we're not looking for the remaining factors. We're looking for the remaining zeros. So the remaining zeros would be negative 2 and positive 1. And then the original 0 that it provided us with was the negative 1. You get 3 zeros for an x to the third. We had 3 factors for an x to the third, so on and so forth. All right. Next one. It says, given 2 is a 0, find the remaining zeros. So this time it starts with x to the fifth. Okay, so something is going to have to give when we divide by 2. So let's see what happens. Let's see what's going on here. We got a few missing terms. We're starting with 16 and 32, but then we're missing the x to the third, and we're missing the x squared, so we have to put in the placeholder zeros there, negative 81, and then the 162. It's a pretty long synthetic division problem. We bring down the 16, then we multiply, and we get 32. We add, we get 0. Okay, I see what's happening here. We're going to have a lot of zeros. 2 times 0 is 0, add 0, 0 again, add 0, multiply, still 0, add negative 81, multiply, we get negative 162, and then we get 0. Okay, so what did we start with? Well, we started with x to the fifth. So this is not going to be x squared, it's going to be x to the fourth. Plus 0x to the third, plus 0x squared, plus 0x minus 81, correct, equaling 0. So this is really just 16x to the fourth minus 81 is equal to 0. Now, from this stage, you could decide that you want to choose another thing to divide by, but you probably are not going to be able to use 2 again. This is also a fourth rootable problem that could kind of get you close to that. Like if we added 81 and divided by 16, then we could fourth root it to get an inkling of what those are going to be. But believe it or not, this is also factorable. This is kind of a perfect square problem, but it's to the fourth power, so we're just going to square root both of these, and we're going to get 4x with a minus 9 and a 4x with a plus 9. Now, because it was to the fourth power, this is going to be x squared and x squared. And now, this is an easier problem to solve because it is squared. When we set it equal to 0 individually, we will be able to solve with either the quadratic formula or we can factor again, but it'd be way easier to just add 9 to both sides and divide by 4, and we get that 9 over 4. But when we square root it, what is the square root of 9 and the square root of 4? Well, that would be a 3 over 2. And because we were the ones square rooting, we have to include the plus or minus. And the square root of 9 was 3, and the square root of 4 was 2. Well, this one over here, the only thing that's going to change is a plus 9, so it is going to be the square root of negative 9 over 4, which means it's plus or minus the 3 over 2, but it's imaginary because it was negative. Okay? The next thing we're going to be doing is something called synthetic substitution. Now, synthetic substitution is something that is a cheat code to if you didn't have a calculator. Okay, so if you wanted to evaluate f of negative 2, the conventional way of evaluating would be to plug in the negative 2 and plug in the negative 2 and plug in the negative 2 for each and every single x. Okay, and that's doable, but if you don't have a calculator, this is going to be really annoying because negative 2 to the fourth power ends up being 81. It's negative 2 times itself 4 times. But then negative 2 to the third power, oh, gee whiz, it's not 81. See? It is 16. Negative 2 to the third power is negative 8. So this would be plus 4 times negative 8. I'm just going to rewrite it. Plus 4 again, and then minus 2. And then you got to do 7 times 16 plus a negative 32 plus a 4 minus 2. That's a lot of effort. And you could type it in your calculator to be going a lot quicker. Just to do it real quick, 7 times 16, then the minus 32, plus 4, and then minus 2. If we did all the math there, I got 82, provided I didn't make any other mistakes. So it's doable. But if we did synthetic substitution, watch what happens here. We're going to plug in negative 2. I'm not going to change the sign. And I'm just going to use synthetic division. We got a 7, a 4. We're missing the x squared, negative 2, and negative 2 again. So we bring down the 7. We got negative 14. Then we add. We get negative 10. Multiply 20. Add 20. multiply negative 40, add, we get negative 42, multiply, we get 84, and then when we add, guess what number we get? 82. Okay, so that tells you that the remainder, quote unquote, would be what you would get if you evaluated it, which is another reason that when it equaled 0, it was a 0. It zeroed out the function. Okay, so this remainder is the solution or the evaluation of f of negative 2. And it tends to be a little bit quicker, but it does prove an interesting point about how synthetic division is actually operating. All right, that's going to do it for this one. Until next time, my friends, I will see y'all later. Bye.